I want to continue with this coding activity, going back to the Taylor series. The Taylor series is a very, very ancient tool in mathematics and also very powerful. It is the foundation of approximation theory. Okay, so that's why I like to come back to it, because you will see it a lot in your career. And the purpose of this activity, if you remember, was to write a Python code that uses the Taylor series to evaluate the exponential function down to a certain error tolerance. If you remember what I said, that the calculator, when you punch in e to the 3, the calculator gives you a number. That's not the true value. That's only an approximate value, because the true value, we really don't know how to compute e to the 3. There's no mathematical machinery to compute that. We have to approximate it with something. Taylor series is one approximation. But then we have to stop somewhere, because the Taylor series is an infinite series. So how does the calculator know where to stop? Turns out that the calculator has a preset tolerance for an error. What is that error? If we don't know the true value, we use the approximate error, right? We cannot do a true error in that case, because we don't know the true value. So we do an approximate error. What is that approximate error? Is the difference between the answer with more terms with the answer with less terms, right? So that's what we will do. We're going to build the Taylor series term by term and take the difference. So 2 terms minus 1 term, 3 terms minus 2 terms, 4 terms minus 3 terms, and so on. And we're going to keep adding terms until we hit a tolerance of 1%, a relative approximate error tolerance. Now you see this Taylor series error notebook with gaps. You can keep that. I'm going to do something different today. We're going to build the code together. So open up your Jupyter notebooks, and I will describe a solution strategy for this problem for you. Okay, so open up your Jupyter notebooks. Start a fresh notebook. And one thing I've seen over the years, that there's a tendency to have one master notebook for the entire course. Do not do that, because one corruption in that notebook, something goes wrong, you copy it, it like goes corrupt, you're done. You lose all the work you've done throughout the course. Make a notebook for each activity. Okay, give it a descriptive name and have 100 notebooks. Fine. Don't put everything into one master notebook. Okay? If you students have done that over the years, they couldn't even run those notebooks, because they were such memory hogs because of all the work that we had to do, and storage in memory. So do a fresh notebook per activity. Okay. I'm trying this year to add a solution strategy for the coding examples, so that you can see what I'm thinking about in my head, sort of a pseudocode, before we get to the computer and start coding. So what I would like to do here is, first, maybe, I would like to write a Python routine. Let's say we call it exponential Taylor series. And that Python routine is going to take an x value, right? That's where we want to evaluate the exponential, and a tolerance, okay, to compute the Taylor series down to that certain tolerance, okay? Now, in that subroutine, we need a variable to store the answer, the Taylor series. Okay, so that's kind of your first hint, is that we need to declare an empty variable. I will call it, guess what? Result. I call all my answers result, so that I know these variables are going to contain the result. And I will initialize it to 0, because it's a summation. And if it's initialized by anything other than 0, it's going to mess up the summation, right? So initialize it to 0, and everything I add to it, it's like an empty bucket. And then I'm going to start adding term 1, term 2, term 3, and so on, until we fill out the Taylor series. Then we need to start adding terms. Clearly, a loop comes to mind. If you haven't thought of that, that's OK. But the purpose of a loop is to do that. Just go count things. Term 1, term 2, term 3, term 4, etc. So we're going to go use a loop. Now, it might not necessarily be a for loop. We'll start with a for loop, and then we will end with a while loop, because it's more efficient. But we'll start with a for loop, and then we will add the terms to the sum iteratively, or we just kept adding term 1, then go to term 2, add, go to term 3, add, etc., etc. Okay? And the value for the nth term is given by the formula. It's x to the power n over n factorial. So we start with term 1, which is 1, and then term 2 is x over 1, term 3 is x squared over 2, and so on. And then we keep adding them. Now, after we add each term, we need to check our error tolerance, right? To know if we reach the tolerance or not. So we need to keep track of the previous term and the new term. So we need another variable called old result, okay, that stores the value from the previous calculation, and then we take the difference with the new calculation. So that difference defines that approximate error, and then we check with the tolerance. We do a simple if statement. If our approximate error is less than 1%, stop, break the loop, okay? Now, once you're done, you return a value. Return what? Result. So every time I declare a routine, I declare the name of the routine, I immediately type return result so that I don't forget to return anything. Now, we're not going to do this here, but this is something for you to consider, is error handling. Okay, what if someone provides a negative tolerance, for example? What if the user provides a tolerance that is very, 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 very small, right? What if the user provides something that, let's assume you're doing the Taylor series of the log function, and they provide a value for x of -2. Well, you can't allow that for the logarithm, right? Because the logarithm is not defined for negative values. So you need to have some error handling. It's always smart to do just to try to check these extreme cases, okay? So let's get our notebooks up and running, and we will work on this together. I will go ahead and create a new notebook here. And let me move this over here. I noticed some of you are using Visual Studio Code for the notebooks. That's great. Whatever platform you're comfortable with, that's fine, as long as it provides you with a notebook. Okay, so let's see in the back. Okay. So let's begin with the solution procedure. First, I want to import NumPy. Okay, import NumPy as MP. So I give it a nickname because I don't want to use the word NumPy every time. Okay. So I will first do it without declaring the function, and then I'll wrap it in the function. Okay, because I want to test things as I go along. So first, I'm going to declare the value of whatever, 3.0 or 2.0, doesn't matter. And then I will declare my result variable. Like we said, this is the empty bucket in which we're going to start adding terms. So result is 0.0, very simple. Okay. And then we will do a loop. Okay, what do you think we're going to be looping over? So it's a Taylor series. It's a summation from 0 to n, or to infinity, right? So what are we looping over? Number of terms, right? Term 1, term 2, term 3. So I need a counter. What do we use for the counter? Range, the range function that we used last time. Okay. Oh, what is range? When in doubt, print it out. Go ahead. Say for I in range 0 to 10, print I. Oh, it's just a counter. Okay, now I remember. Okay, great. Right, so let's do a range for n. I'm going to call it n now because n terms. Right, spice things up a little bit. I'm very good with nomenclature, with naming things, you'll see. For n in range, going from 0 to what? How many terms should we add to the Taylor series? 10? What if we don't hit the tolerance in 10 terms? 100? What if I can find a function where 100 terms are not enough?
Keep doing it until you get the required, and just checking what your error is until you get the required error.
Okay. So that's going to be the while loop. So how about, yes?
Can we do like an else if statement where it's like it keeps looping?
Yes, that would be the while loop. So you're all onto it. Mm-hmm. But what is n?
Well, just the next term.
Yeah, but the for loop needs to know like where it's starting and where it's ending, right? Okay. So without complicating things, I'm going to start with the for loop, and for the sake of discussion right now, I'm just going to put 10,000 terms. 10,000 is not enough. Might not be enough. Okay? But I will check in the for loop where to break the loop. Eventually, we're going to solve this problem with a while loop. But I want to show you the for loop and how the while loop is going to be more effective than this. So let's say, 10,000 terms. Okay? Right? For n, going from 0 to 10,000 terms. Right? So then we're going to start by saying result is equal to result plus 1 over, I need the factorial function. Well, the factorial function comes from math. Okay, import math. All right. So you didn't know that. If you didn't know that, you cannot, how do you get factorial in Python? You go Google, how do you get factorial in Python? It will tell you from the math module. So import math and move on with life. Okay, so I want 1 over math dot factorial, okay, of n times x to the power n. Okay? Times x to the power n. So is there something wrong with this line? Have you seen this before? A is equal a plus 1. Okay. So if you know what it, if you don't know what it is, please raise your hand. Okay. So this is not a math equation. In math, if you write x is equal x plus 1, doesn't make sense. But in programming, this is not the case. This is not an equation. What an equal sign in programming, what an equal sign is saying, new memory is equal to old memory plus something. So the value in result, the new value in result, is equal to the old value in result plus whatever you want to do to it. It's not a mathematical statement in the sense x equal x plus 1. This is like saying the new value that I'm going to put in result is equal to the existing value in result plus something. So I'm updating on the spot. Okay? That's all I'm doing here. So now think about it. If we start with result equals 0, so we go in here, n equals 0. This is already 0. Okay? And then 1 over 0 factorial, that's 1. Times x to the power 0, that's 1. So it gives us result equal 1. That's indeed the formula, the first term in the Taylor series. Agreed? And then we keep adding terms. OK, are you in doubt of this? Let's print it. So I'm just going to do 3 terms. Okay? And then I'm going to print result. Okay? It started with 1. Then it added 4, became 4, and then 8.5. So it's doing something. It's adding 1 term at a time. Okay? I don't want to run it for 10,000 because it will take forever. I need it to stop somewhere. OK. So now that's great. And I need it to stop somewhere. So I need it to define an error. So I'm going to write some pseudocode here and say error is equal the absolute value of the formula is new approximation, new minus old over new, right? So that's my error definition times 100. Now, my new values are actually results, right? But what do I have where do I get my old value from? I simply create a new variable over here. Before I update result, I make a copy of it in another variable. So when I enter the loop, the result contains something. So when I enter the loop, initially result is 0. Then it gets filled up with something. I end the loop with the print, and then I go back here. Result still carries a value. So I'm going to hijack it and store that value in another variable. And I'm going to call it old result. Old, for lack of imagination. Okay. So what this is doing is storing the existing value of result into another variable. Okay? So now I can do result minus old result over result times 100. That gives me an error.
Is there any difference between the like np dot absolute and just like the top?
np.absolute works on arrays, but it has a different kind of definition on arrays. So I'd like to use it all the time. I prefer to use it just so that because mixing NumPy arrays, non-NumPy arrays, so it's safer to do it with NumPy absolute. Okay. Just accept it on point, like taking an old value of result, putting it in a variable so that I have the previous value. I update result, and now I can formulate an error. Okay, I can compute an error. Now this is the punchline. If error less than my tolerance, or what is tolerance? I'm going to declare it here. Tolerance is 1%, so 1 over 100. Okay? That's my tolerance, 1% error. Okay? Now notice the errors are expressed in percentages here, right? So if error is less than tolerance, there's this really neat thing in for loops in all programming languages. It's like you want to break a for loop. You want to stop it for some reason. This is one reason. We reach our desired tolerance. There's a way to get out of the loop, and it says simply is break. Just type break. Changes color, right? So it means we're on to something. Okay, so now we're done. Okay. Do you think it's going to work? I don't know. Let's try it with 10 terms. Okay, good. All right, so I need to do some more stats on this to know how many terms it took. So if I print n, in 9 terms, okay, let's do 20 terms. In 12 terms, it reached the tolerance. Okay? So in 12 terms, it reached this value. Now, if you punch this into the calculator, so np.exponential, so exponential to the 3 on your calculator should be 20.0852 or something, right? So let's run some more stats on this and say, okay, let's dig into it a little bit more. Okay. Say, print error with n terms is equal to e %. Okay. Error. Okay, is equal to error. Okay. So error was 0 turns 100%, obviously, then goes down 75, et cetera, and then it hits all the way down to 1% error. Then, yeah.
So when we calculated the error, we converted that into a percent by multiplying by 100, right?
Yes.
Okay, but then our tolerance is
Wasn't it
over 100.
1%? Yeah. So that's 1%.
But wouldn't that convert that 1% into a decimal when we have converted our error into?
That's right. That makes sense. Thank you. You're right. Okay, thank you. That's a minor theoretical error. I get docked 20%, okay? So, okay. Now you see as we add more terms, we are decreasing our error as expected in the Taylor series. And it's a nice way to stop it, right? Now, if you change the x value, it might take more terms to converge. If you go to e to the power 10, it's going to take 18 terms with e to the power 10. So there's no guarantee you are going to converge even with 10,000 terms or 100,000 terms. So we need a better mechanism to stop it. Rather than specifying a fixed number of terms, we needed to just keep adding terms until it hits the tolerance. Okay? But there's a problem with that as well, because what if it never approaches that tolerance? Right? When do you stop? So the advantage of the for loop is that, you know what? I'm going to allow this calculation to a maximum of 10,000 terms, and I will report whatever value I get, even if we don't hit the tolerance. Okay, so that's a fail-safe mechanism. Okay. The other approach would be to not specify the number of terms. So how do we do that? We use the while loop. Have you done while loops before? Okay. Okay. So what is the advantage of the while loop based on what you know about while loops? Pardon me? Runs forever until, which is risky, right? If you run it forever and there's no stopping criterion, you will get in trouble. So that's the risky thing about while loops, right? The advantage, another critical advantage of the while loop is that, and this doesn't apply for small problems like this, but once you do problems with billions of equations and hundreds of millions of equations, every time you're going in the for loop, you are stopping here to make a test. Check, check, check. Imagine the for loop, you're running, then check, running, check, running, check. Once a for loop gets started, it's really fast. When you put an if statement inside the for loop, you're killing its momentum. Demonstrably, you're killing its momentum. The while loop is a combined for loop and if statement that's a little bit faster than you doing a for loop and an if statement. So if the for loop with if statement is like this, the while loop is it's a little faster. Okay? It's more efficient. But in the end, it is a combined for loop and if statement. Because think about it verbally. While something is true, do this. When that thing is not true anymore, it will automatically stop. That's the idea of the while loop. It's a combination of for loop and if statement. So in our case, while our error is greater than the tolerance, keep adding terms. Once the error hits the tolerance or below, the while loop will stop automatically. You don't even need to have an if statement. You don't even need to have an if statement, okay? So let's do it. Okay, so I'm going to copy and paste these things over here and just clean them up. So, okay, we'll start. I am going to start with so for the while loop, the idea is going to be while error is greater than my tolerance. That's how it looks like. Do something, okay? Recompute error, and then that's it. That's all you need to do. You have to recompute the error every time. But the while loop automatically does that test for you, okay? So I will still take old result equal to result, because I need to evaluate an error, and I will take this and this and this. So I'll take all of these things, okay, which is great. Result, etc. Okay, and that's it. That's it. Was there an if statement? Yes, it is embedded in the while loop. Because the while loop is saying while the error is greater than tolerance. Where is error calculated? It's here. So the while loop automatically observes and monitors this variable here. So whatever goes in the argument for the while loop needs to be updated inside here. If you don't update this, you'll get a while loop forever. You will crash your computer. Okay, you have to restart your Jupyter notebook. I'm not going to demonstrate that here. Okay. Okay. I'm going to catch up, and we'll run it. Okay. What did it do? Print it. Okay. So it didn't do anything. Why? Because I have not declared error in the beginning. I didn't initialize the variable error. So when it came in here, okay, let me kill the notebook and I'll show you what I'm saying. So I'm going to restart the notebook. I'm going to import this and only go to the end cell. It's going to throw an error here. Error is not defined. Okay, so I need to declare the variable error. So what do you think we should initialize the error to? 100%. Yes. Even more. I'm going to put a very large number there to make sure that I'm always larger than the tolerance. So your colleague said, initially when we enter the for loop, we need to make sure that the error is actually greater than the tolerance. Okay? So that we actually enter the for loop. So you could say error is equal, 100, or tolerance plus 10. It's always bigger than the tolerance. Okay? All right, so now it threw another error. N is not defined. Oh, crap, we need a counter. Okay, let's add a counter because we need this n factorial, right? So I'm going to start initialize a variable here, n equals 0. And then in the while loop, I'm going to start augmenting n. And I'm going to say n is equal to n plus 1, right? So we go in, and we augment our counter manually. So it takes more lines of code in the while loop, but it's more efficient than the for loop and an if statement. If you need an if statement in your for loop, consider doing it with a while loop. Okay, it's worth the effort. All right, let's see. Is this going to work now? Yay, it worked. Okay. Did something. I'm going to go back to the number 3 here. X equals 3. Okay. So in 9 terms, it hit the tolerance. Okay. It took print n. I'm going to say it took n terms to achieve tolerance of tol percent. Okay? There you go. This way? Yes?
Why isn't our while loop the same as our other loop? The other one, it took 8 turns, and this one took.
For x equals 3, 8 terms. This one, it took 9 terms because it accounted for this n plus 1. So we probably could report actually n minus 1 right here. So good point. That's not a minor theoretical error. It's a minor kind of programming error, so like 2%. Okay. So I've lost 22% today, but thank you for correcting me. And I'm doing this on the fly with you. So to show you that I make errors too, yes?
So right there you have like to achieve a tolerance of 1%, there are tolerances less than 1.
Yeah. So that's so it's less, that's better than 1%, right? So think of it as you can get exactly 1%, right? Once you hit below 1%, you're happy with that, right? Yes. Your other question?
Oh, it was just like, how do you type in like less than or equal to?
In Python, you just less than or equal.
Like,
You want,
less than and then equal.
yeah. So I don't trust the equal unless you're doing algebra. So here's my rant. When you're dealing with floats, there's no equal. Because if even one insignificant digit that to the computer appears to be significant, there's no concept of equal. There's always a bound. So I only do equal or greater than equal when we're doing like algebra, when we're doing integer, exact numbers. But with floating points, don't use greater than or equal. The equal is meaningless. It might actually get you in trouble. So a better guarantee is greater than. Okay? So that's why I use that. Okay. All right, so this should be it for the Taylor series. We've successfully prevented it from taking over the world with my silly joke. Okay. Come on, I was like so impressed by Dolly for doing this Taylor series taking over the world. I was it figured it out. You know, it's like this big, gigantic Taylor series eating the globe. And there's like some, if you notice here, there's like some explosions going on here, right? It's you know, thinking of something. OK. So some code summary. This is what you need to know about errors. Now we get to the more qualitative part of this section. I don't think I can finish all the discussion on errors today. So some of it might spill over for Tuesday. But that's how we compute errors in practice. So the relative approximate error is going to be a cornerstone of many of the things we will be doing as we move forward. Okay, we're going to be doing iterative methods. We're going to be doing nonlinear solvers. We will need to check our tolerance every time, and we will be using the relative approximate error for that. All right. I'll go back to that slide I put in early on in the lecture, talking about sources of errors. If you remember, there were modeling errors, programming errors, like the one I just committed. I printed n rather than n minus 1 for the, that's, you know, a little programming error. But then numerical errors, where we are concerned with, are primarily round-off and truncation errors. And round-off errors, you saw the example from the Ariane rocket, where this conversion between a 48-bit or whatever, 32-bit to 16-bit precision, excuse me, it lost some precision and messed everything up. Almost always, disasters related to numerical methods have to do with some silly round-off errors. Okay? Luckily, in today's world with modern computers, that's less likely of an issue because we have such high bit bandwidths in our computers. We're like up to 256 bits now. So we can represent all very, very large numbers. Okay, so that's not an issue usually. So for example, by default, Python defaults its flows to 64 bits of precision. That's very, very good. Okay. So we'll start with round-off errors, and I'll give you just a rough idea of how numbers are represented in computers and what round-off is. It's not an exact description because I don't want to go into detail into the theory of bits and binary numbers. That's, you know, not that relevant to what we need to do. And computers represent numbers up to a finite precision, like you heard from the Ariane discussion. And think of the different digits in a number as fitting into like little buckets on the computer memory. Okay? Now, they're not represented exactly like that because we need to convert them to binary first, and it's the binary bits, the 0, 1, 1, 0, 0, 1, 1, 1, etc., that are stored into blocks in the memory. Okay? Now, 64 bits have 64 blocks in memory. 128-bit computers have 128 blocks, right? And you can imagine how many numbers you can represent with those. 16 bits has less, all right? So then what happens, so if you're representing like this number, 0.154, imagine that each digit is fitting in a bucket, okay? Now, when there are less bits than there are significant digits, the number is chopped or rounded. So suppose you have a 5-bit computer and you shrink that number, putting it in here, it will only represent the first 5 significant digits, okay, in the number, all right? Because it needs also the decimal point, all right? So, you know, it rounds it, either rounds it or chops it, which is an error, right? You thought you were representing a number, now you're actually representing something else. Now, this error is called round-off error. Here's the definition. It's the result of the inability of computers to represent all significant digits as a number. It is therefore the difference between the actual value of a number and its rounded representation. Clearly, the more bits you have, the more significant digits you can represent. And there are some common floating point numbers that, you know, I've talked about 16 bits, 32, 64, 128. You know, my first computer had 8 bits in it. I had like it had a 2 megabyte hard drive. It was this big. It's called the Bigfoot, you know, by Western Digital. Still exists, that company. So anyway, Python usually defaults to 64 bits for floats. Okay? It's a very, very good accuracy. Now, modern programming languages will allow you to represent, even if your computer fundamentally is not 64 bits or not 128 bits. It has a trick to allow you to represent larger bit numbers, okay? But you have to tell it. There's an example that I put here in the slides. Now, in reality, I mentioned the binary representation. In reality, first, the number in decimal space is first converted into binary, and then the binary are represented. Why we can only put the binary? Because in computers you have two states, either on or off. So if you think about a series of transistors in a microchip, right, in the memory, you can either have a state of, charged or not charged. That's it. So 0 or 1, digital computers, okay? I'm not going to do this coding activity, but I'll give you the description of what it is. And the idea is use Python to sum the number 10 to the minus 5 100,000 times. Now, analytically, in your mind, 10 to the minus 5, if you add it 100,000 times, it will be equal exactly to 1.0, exactly. Okay? That's exact mathematics. However, you'll be surprised, like we did the problem early on, x plus x minus x minus x minus 1. That's not going to be the case. And you will see a difference between representing that summation and that number as a 16-bit float, 32, 64, or 128-bit floats. This is how you would create different precisions in Python. Don't do that in your research or on your career. This is only for very specific use and for demonstration use, like in this class, okay? In Python, you declare a number. It's by default a 64-bit number unless your distribution says otherwise, okay? So here's, my plan would be the solution strategy is to define the number 10 to the minus 5 and then declare it in all of these precisions in a 16-bit representation, in a 32-bit, 64, and 128 bits, and so on. Now, if you go ahead and you just do a for loop and add the number, you're welcome to try this code. You just copy paste this from the PDF and you print it. What I'm doing here, I'm just simply taking that number, x, and I'm converting it to 16-bit float, 32-bit, 64-bit, and 128 bits, okay? And then I'm adding it 100,000 times, okay? Doing for the half precision or 16-bit precision, single precision, which is 32-bit precision, double precision, which is 64-bit precision, and quadruple precision, which is 128-bit precision. And I'm comparing it with the true value. And look at that. With the 16-bit representation, you get an error of 0.13%. And then when you go to 32 bits, the error drops to around 10 to the minus 6. Then with 64 bits, really great. There's still an error, though, 10 to the minus 10. And then finally, with 128 bits, 10 to the minus 13. But there's still an error. It's never exactly equal to 1. Okay? Round-off errors, they accumulate. That's the problem with them. If you commit one round-off error with like a single calculation, it's usually insignificant. But when you have a procedure where you're adding the same thing over and over and over and over again, it's going to drift, and it will drift significantly. Okay, just like that example, 100,000. You can do the example with 10 to the minus 7, for example, and add it, 10 million times. You'll see an even bigger error. All right, round-off errors in real life. We talked about the example of the Ariane rocket. There are a few others. This one I like to discuss. And it is on your homework 2 assignment. It has to do with the Patriot missile defense system and an incident that happened in 1991. Okay, so the Patriot defense system was, and kind of still is, it was a clear innovation by the US military to target rockets that are attacking military bases. So it consists of a few radars and scanners that constantly scan the sky. If they see a bird, they don't shoot it, right? If you see an airplane, they don't shoot it. But if you see a rocket, there's like internal mechanisms saying, oh, this is probably a rocket that's going really fast. And they were primarily concerned with Scud missiles from the Iraqi military, right? So they were shooting these rockets. They go like Mach 10 or something. They're really fast, and they do a lot of damage, okay? And they constantly scan the sky. Once they detect a missile, they shoot it down. especially if it's within range. If it's out of range, like, whatever, go, you know. But if it's within range, they would shoot it down, okay? Similar to the Iron Dome right now. And so, however, on February 25 in 1991, this is taken from Wikipedia, straight out of Wikipedia, an Iraqi Scud missile hit the barracks in Dhahran in Saudi Arabia, killing 28 soldiers from the US Army's 14th detachment, okay? A government investigation revealed that the failed intercept at Dhahran had been caused by a software error in the system's handling of timestamps. The Patriot missile battery at Dhahran had been in operation for 100 hours, by which the time system's internal clock had drifted by 1/3 of a second. Why did it drift? I'll explain that in the homework. It's because they were converting 48 bits to 16 bits, and over 100 hours, it was taking a timestamp every millisecond. Over 100 hours, convert that to milliseconds. That's, you know, hundreds of thousands of cycles. And that minor error accumulated and resulted in 1/3 of a second error. Now imagine a rocket flying at 1,500 meters per second, and a third of a second error could tell you the rocket was over here or versus over there. So it thought that the rocket was already past the barracks, whereas it was not past the barracks, and it didn't engage, and it had destroyed the whole facility. And anyway, so the radar system had successfully detected so by which the timestamp internal clock had drifted by 1/3 of a second. Due to the missile's speed, this was equivalent to a missed distance of about 600 meters, okay? 600 meters. So the missile was going about 1,675 meters per second, and 1/3 of a second, that's about 600-meter drift. The radar system successfully detected the Scud and predicted where to look for it next. However, the timestamp of the two radar pulses were converted to floating point differently. One correctly, but the other introducing an error proportionate to the operation, 100 hours, caused by a truncation, what computer science people call truncation, we call round-off. Okay, I mentioned that last time. So in computer science, they call that truncation. It's a round-off error. By the round-off error in a 24-bit fixed point register. As a result, the difference between the two pulses was wrong, so the system looked in the wrong part of the sky, and the node target, the detection was, thought to be spurious. Anyway, so that was bad. You'll solve this problem in your homework assignment. A few other examples. Patriot missile. There's a web page dedicated to these round-off errors. There's one in the Vancouver Stock Exchange. And it chopped the stock tracking index to 3 decimal points, producing a loss of 500 points in the index. That's like a drop of like 50% of your investments. You're like people lost it there. So just for these tiny little errors. Okay. Now, should you worry? Not really if you're in engineering, because most engineering and mathematical systems will cancel out the error or wash it away due to the dynamics of the problem. So typically, if you commit the error in one cycle, doesn't accumulate, that's rarely an issue. And trust me, there's one of those errors in any software code out there. It's amazing that the world operates, that our GPSs takes us where we want, or like you click on Amazon, this is my address. Like it's all a miracle. But and I don't know, like frankly, when you are in it, like I have no idea how this works. Like it's amazing that it actually works at all. So. But don't worry about it, but don't blindly trust numbers just because a computer gave them to you, okay? The fact that it's a computer can be wrong. I'll talk about truncation error and we'll wrap it up next Tuesday. I have 5 more minutes. Okay. Now, truncation error is the other type of numerical error we are concerned with. And truncation error, as we define it in math and in engineering, is the result of taking a very big mathematical formula that's going to take over the world and truncating it. Chopping it at some point and say, like the Taylor series, we can't do an infinite number of terms. We have to stop at 20 terms, at 50 terms. What happened to all the remaining terms? Well, that's going to be called the truncation error. It's the difference between what would have been the true value and the value we actually computed. That is the truncation error. Now, we don't know the true value, but we can assess the truncation error because we know we stopped at 20 terms. All the remaining terms are going to be the truncation error. Then mathematicians come in and say, oh, all those terms are bounded by this and that. So we have an idea about our mathematical methods. So the truncated Taylor series we presented earlier are an example of where truncation error shows up. And this is my note, some computer science circles. Again, truncation error refers to chopping a number. We call that rounding off, round off error. OK, so I'll spend some time on the Taylor theorem. Let me do a sanity check. Did you see the Taylor series in your calculus, in your high school? OK, good. So this will be a refresher. The Taylor theorem states that, and I might explain it differently from what you learned it. And that's OK. Different diversity of thought kind of like actually is enriching. So the way I think about the Taylor series is that given all function values at one point, so imagine you're trying to evaluate a quantity, but you only, a function, OK? You only know the value of that function and all its derivatives at one point. The Taylor theorem tells you in the vicinity of that point, just right next to it, you can make a prediction of what that function value is going to be. So in this case, if I know everything about the function at point A, so I know f of a, I know f prime of a, I know f double prime of a, and so on, then I can predict the function value at x. What is x? Some arbitrary point in the vicinity of a. I can predict the function value at that point without knowing all the function values at that point. So by only knowing what happens at a, I can predict at what happens at some arbitrary point in the vicinity of a. How far away from a? Well, it depends how much information I have about the function. What if I only have f and f prime about a, at a? Then I cannot really travel that far away from a, but I can get a pretty darn good approximation near a. We'll demonstrate that on Tuesday. I'll show you how those individual terms that we added in the Taylor series, how they approximate the function in the vicinity of a. Okay? And this is the formula for the theorem. Typically, you see these formulas applied at a equals 0, just because it's simple and easy. But that's not the only way we could do it. We could do the Taylor series at any point. So for example, this would be the Taylor series for the exponential function in the vicinity of 0, be e to the 0 plus derivative of e to the x, which is e to the x, also as f prime at 0, and so on. So that's where you get this formula from. Okay? So next Tuesday, we will go ahead and do this Taylor series, but at a different point, and we'll plot it. We'll plot the different terms, see how it approximates things. Thank you for your attention, and have a great weekend. Look forward to seeing you on Tuesday.